Okay, I'm extraordinarily pleased to be able to preside at the award symposium for the Pittsburgh Spectroscopy Award. We have the good fortune to be presenting this award today to Geraldine Richmond from the chemistry department, University of Oregon. And so this is an award that she richly deserves for her pioneering achievements in spectroscopy and chemistry. Just let me tell you a little bit about Geraldine. Some of the people who'll be speaking know a lot more details about her, but I know that she's the presidential chair and professor of chemistry at the University of Oregon, and that she's a member of the National Academy of Sciences. She has a very long list of awards, also very richly deserved, and I will share with you her CV if you come up and read this tome. And so these are the introductory remarks. The next step is to present her with the 2014 Pittsburgh Spectroscopy Award, and that will be done by Manny Miller, who's the chairman of the Spectroscopy Society of Pittsburgh. So Manny, if you'll come up.
Well, thank you, Sandy. First of all, I want to thank Dr. Sandy Asher and his committee for making such an excellent choice this year for the Pittsburgh Spectroscopy Award. As Sandy mentioned, there's many accolades and accomplishments for Dr. Geraldine Richmond. But if I would go through them all, I think I would take most of her talk away from her, and I certainly don't want to do that. But I did want to mention one thing besides all the previous awards she has received and all the other research accomplishments. One of the things I think that she is most proud of, and she has presented numerous awards and is an organization known as COACH, and it's dealing with women in science. And through their networking, seminars, workshops, she has affected the lives of, I'd say, over 8,000 different women in science. And besides, as I said, her research endeavors, she's greatly needs to be recognized for that, too. And she has gotten, among other awards, a presidential award for her efforts in dealing with that organization. And without any further ado, I'm going to present the 2014 Pittsburgh Spectroscopy Award to Dr. Geraldine Richmond. And thank you. Congratulations.
Thank you.
And there's the award right there, by the way.
We did pictures. We did pictures. Should I start?
So do you want to say just a few things and then we'll wait till the official start time for your seminar?
What time is it supposed to start?
It's supposed to start at 1:40, I think. So at the moment, we're 6 minutes.
Okay. Actually, I would like to. So Sandy has just informed me that the official talk doesn't start until 1:40, so I have 6 minutes to talk. Which is like
3 minutes.
3 minutes to talk. I thought you meant I had to put my whole talk in 6 minutes. I was just kidding. So I do, I'm going to say a little bit about COACH. I'll take the 5 minutes to do that because COACH really needs your help. And many of you, some of you in the audience know that Jean Pemberton and I started an organization called COACH 15 years ago, and it was to help advance the careers of women scientists in the United States. And through COACH, in which Mary Worth is here and Sharon Neal is part of the advisory board, we have developed workshops that we run before American Chemical Society meetings, which we've done for over 15 years, and that's how the number has now stretched to over 10,000 women scientists that we have met, that we've worked with not only at ACS meetings but also APS meetings. And I'm delighted to see there's a special symposium on Thursday for women in spectroscopy here. And by the way, I must say it's nice to be introduced in a group where people can actually pronounce spectroscopy rather than fumble it. And the reason that we need your help is that because in the last 3 years, COACH has been working very actively in developing countries to help scientists in developing countries advance their skills. With projects in many countries in Africa, including Kenya, Mozambique, Tunisia, Morocco, Algeria, South Africa, Botswana, and also in many countries in Asia and Latin America. And the way that we can use your help is that many of the scientists that we meet in these countries, and it's not just women, it's men also, are really trying hard to make connections with scientists in the United States, and particularly in the area of analytical chemistry, of which there's a lot of interest in coupling with your graduate students as well as faculty. And so if you have any interest at all in having your students or you getting involved with scientists in those countries, we have wonderful connections and wonderful research projects that they're struggling to conduct on issues of global importance, whether it have to do with water or energy or the environment. So please just email me if you have an interest. We can figure out some way that you can get involved, either over email or possibly getting you involved in some collaborative effort. Much of the work we're doing is supported by the State Department as well as USAID. We don't have much money, but we have a lot of energy and growing contacts. So sorry to have taken my 6 minutes for something that's not quite scientific, but I think it is something that many of you could see an interest in because it's truly very important. Are we ready? 3 minutes.
You didn't talk long.
Okay, does anyone have any questions on that? Otherwise, you can turn and introduce yourself to the person next to you. Christy. Yeah. So Christy came to us for the project in North Africa that we've been working with on energy, water, and the environment. Yes, we have a number of scientific collaborations that have started, particularly in Brazil. Some of the scientists we're working with there. But we are also going back into Mombasa, Kenya in June. And there we will be running workshops, and I'm particularly interested in women scientists that work in the area of water from the U.S., because we'll take over a team of about 6 women to work at there. They have an organization called CNAC, which is the African Network of Analytical Chemists, and so that's another set of collaborations that are continuing. Claire Mahoro has a combination with Jay Moringi, who's at Kenyatta University, and so forth. Any other questions? Okay, I'm ready. Okay, now science. That worked. Great. Okay. So, I'm excited to, well, first of all, let me say how truly delighted and honored I am to be selected for this award. The people that have won it in the past are amazing. And one in particular that helped me in the very early stages of my career, and that would be Bill Fateley. And not everybody laughed in the audience because he was a jokester, but he was also just an incredibly kind and giving individual. And I met him when I was an undergraduate at Kansas State University. He had just moved there and really wondered what he was doing in Kansas. But it was a wonderful time, and he was very influential in my life, and then connected me at a later time through various ways, good or bad, with Bruce Chase, who has promised me he's not going to tell bad stories about me when he gives his talk. So that was to set you up, Bruce. Okay, so today I want to tell you about some work that's been going on in our laboratory, and we keep digging a little bit deeper into it all the time. So I'm excited to be able to tell you where we are at this point. And that has to do with understanding macromolecular absorption at liquid interfaces, and particularly at the oil-water interface. So scientifically, this junction is relatively unexplored, but it's important because that's an interface where you can do chemistry. You can also understand. It's a model for understanding biological systems because they are water next to hydrophobic media, and for exploring many interesting properties of water next to a hydrophobic surface, including the very recent discovery of unique properties of water next to nanoparticles and nanotubes that just came out in Science. It's also important for many environmental commercial products, paints, oil in your detergents in your oil cleansers, and also for trying to come up with the products for oil remediation. So the focus of this talk is on three questions: why, how, and what. And in particular, why are the molecular properties of this interface so unique? I'm going to summarize very briefly what we know about this liquid-liquid interface from our spectroscopy measurements and our theoretical measurements. And then how do these special properties of that interface influence the absorption? And today I'm going to talk in particular about polyelectrolyte absorption. And with that polyelectrolyte absorption, what is the interplay between charge and hydrophobicity? Because you have two media, one which is very polar and one which is very nonpolar. And so anything that goes there is going to be either partially attracted to that hydrophobic region or have a charge or a polar group that would be attracted to the aqueous phase. And so that interplay between charge and hydrophobicity is very intriguing for us. So the methods we use are vibrational sum frequency spectroscopy. I'm not going to go into the details of this because it's a fairly well-established technique at this point. But basically, we're measuring the vibrational spectroscopy of interfacial molecules at this oil-water interface using total internal reflection sum frequency spectroscopy. The rules behind this is that because it's a second-order process, it can only happen where there's broken symmetry. That makes it very interface specific. And from a spectroscopy point of view, the molecules that we see have to be both Raman and IR active, and they also have to be oriented. Otherwise, we won't see them. We also do surface tension measurements by either Wilhelmy plate or the pendant drop method, depending on the system that we're working with. And in this case, what you're going to see is I'm going to talk about how the interfacial tension changes as the polymer goes there, interfacial tension going down as it goes to the interface, either as a function of time or concentration. And which is another important aspect of the work that we do are the molecular dynamic simulations. The spectroscopy is very informative and very helpful. But we oftentimes are missing part of the picture unless we augment that with molecular dynamic simulations. Now, I come to this field of simulations as never really trusting them before, and so the way I feel that the way I get trust in these simulations is what we do is we do a simulation of the system, and we have measurables from the experiment, and if we can simulate something that we see in the experiment, that gives us confidence to go further with regards to the simulations. And I'll give you an example of this in this talk. Okay, so what have we learned about the oil-water interface that pertains to what I'm going to talk about today? And this has to do with both the experiments and simulations. What we've learned is that the weakest hydrogen bonding at the interface occurs right at the interface where you have water molecules that bond to only one other water molecules, but even more importantly, they weakly bond to the organic phase, which sets them up into an orientation like you can see right there. So it's got one OH in the aqueous phase and one in the oil phase. That shows up as a free OH bond. If you go a couple of angstroms deeper in the interface, the hydrogen bonding gets a little bit stronger. And then strongest when you get, and again, for these measurements, these water molecules are oriented down to about 8 or 9 angstroms into the aqueous phase, and then become more random in nature, where you have the more stronger hydrogen bonding and random. You also have water monomers that exist into the organic phase, and they are oriented down to about 10 or 12 angstroms into the organic phase as they penetrate in. So what I'm describing to you is an interface that actually has somewhat of an interfacial field which is there. And that interfacial field is set up by this interaction between the water and the oil and the orientation of these molecules. And so what that does is then help to drive ions into that interfacial region, which you can appreciate then is important for understanding biological systems. But it's also important for understanding anything else that goes to that interface because that field is there. Oops. So how does this field influence the absorption of macromolecules at that interface? That's the point I'm going to be talking about next. And so we've chosen to use polyelectrolytes as one of the systems that we've been using to study this interface further. We've done a series of different surfactants, and polyelectrolytes is the next step. Now, the reason I have teeth up there is because polyelectrolytes are commonly used now as coatings to protect teeth. And also, polyelectrolytes are in a lot of different products, including paints. They've been studied a lot in bulk solution, and we know from 30 years of studying polyelectrolytes in bulk solution that they can be in a coiled configuration when they're uncharged. They can also be, when charged, they can spread out more because there's repulsive interaction between the charge. So a lot of literature with regards to polyelectrolytes in bulk. Oops, I keep popping too fast. But little is known about their behavior at an oil-water interface where, of course, most of their applications are. If you're trying to find some kind of a dispersant, it's going to be its interactions at an oil-water interface is most important. And so that's why we've chosen to study them. So what else is not known is this interplay between the charge with dissolvation and hydrophobicity, because as this polymer gets more and more charges around it, it's more likely to go to the aqueous phase. And as it loses its charge, it's more likely to be hydrophobic. And so what we do in these studies is to understand the charging effects. We're going to use pH studies, and I'll show you in a moment with what polyelectrolytes, but pH studies which allow us to alter the charge. And, from a physics perspective, it's basically being able to turn on and off the charge on this polymer, and also to add salts, which then have electrostatic or complexation binding with the polyelectrolyte. So we'll do charging studies, and then we also do studies to understand how the backbone plays out in all of this, chain rigidity as well as flexibility, by doing isomer and size studies. So those are the kinds of studies that I'm going to talk about to understand this adsorption. So I'm going to focus on carboxylate-containing polyelectrolytes. These are particularly interesting because they have weak acidic groups on them. And so that we know that at low pH, they're protonated. And in this case, from a spectroscopy point of view, we're going to be looking at the CO modes around 1730. Then when it becomes deprotonated, we can look in the 1410 wave number region. So that's why we're going to probe whether they're there or not. And remember, if we see them there, they have to be oriented, because if they're disoriented, we won't be able to pick it up. And then the CH modes will be able to look at the backbone and also the water region in the 3000 wave number region. The pKa in bulk solution is about 5.5. So the first case I'm going to tell you about is PAA, polyacrylic acid, and then the second case will be polymethyl acrylic acid. And the interface is carbonate water. So the first question is, does PAA adsorb? Well, the answer is yes. At a pH less than 4, you find very sharp signals from both the CO mode as well as the backbone modes. So that tells us that the PAA does adsorb a very strong orientation, which was remarkable to us because that peak is very, very sharp relative to a lot of the other surfactants we've studied with carboxylic acid, so that the sharper that peak is, the more defined its solvation is, and so it tells you that it's highly oriented. But not at a pH greater than 4.5. So between 4 and 4.5, it completely comes off of the interface. And so you can see this with the spectroscopy, the top figure up there, which shows the CO mode, where from 1.5 to 4, you have strong signal, and that signal does not vary with pH. And then 4.5 to 10, it's gone. And if you go in the region where you're looking at the carboxylate mode, you see nothing. So if you look at this, the titration, sort of the titration curve for this, for the sum frequency amplitude, what you find is that the signal stays high and then very rapidly drops down and stays to 0. So it's very sharp, indicating there's some type of cooperativity that's going on, but we'll come back to that. The surface tension measurements are completely consistent with that. If it goes to the interface, you would see the surface tension drop, and that's indeed what you see in this region here, and between 1.5 and 4, but between 4.5 and 10, the surface tension stays high. And so it's interesting because the strong adsorption is in the acid form, where the acid form in bulk solution is more of a coiled configuration. There's complete desorption, and the way that we see that once you go to higher pH, and the way that we see that when it then becomes charged, is that this is now the CH region. This is 2 to 3.5, and then this is offset a bit for pH 4. You can see the CH modes. But then you get up to 4.5, and this is actually the water spectrum of carbon tet water. And if there's even a tiny amount of anything there, this spectrum would show CH modes. And you can see a little tiny blip right here, but there's basically nothing there. And again, this spectrum is very sensitive to that. So very strong adsorption at low pH, and then it comes off. But the most interesting part of this data is in the time scale. So these spectra that I've shown you here, as well as the spectrum in the CO region, are taken within a minute, and they don't change at all. Yet the time dependence shows that the surface tension is dropping well beyond a minute and continues to drop over time. So there's continued adsorption at the interface, even though the spectrum doesn't show anything. And so what that indicates is that the first PAA units adsorbed to the interface and are highly ordered, and then with time, PAA adsorbs with random orientation. And so that first layer goes down highly ordered, and the rest comes down with random orientation. And only a small amount goes down. And so when you go back to think about what I described with regards to what that oil-water interface is, we believe that a strong component of that is that field that is there that helps order that first layer, and then subsequent layers come on because of hydrophobic interactions. You also see an interfacial charge reduction in the water, so the water signal that shows strong orientation largely goes away, and so and that's because you have this reduction because of the polarity comes in and into the interface. Desorption is immediate and at relatively low pH, as I noticed, 4.5. Remember I said the pKa is around 5.5. And this is because increased charge on the polymer leads to a greater solvation, which then pulls it into the aqueous case. So there must be cooperative processes which facilitate the desorption in this narrow pH range. And what do I mean by that is that something has to be going on where the carboxylic acids are playing around with each other to induce a lot of them to be dissociated and solvate in regions of the polymer. But we'll come back to that in a moment to try to prove something like that. Oops. So, questions. What factors contribute to this disordered layering? And what are the cooperative processes that lead to this desorption? So how we've gone after this is to understand, first of all, is the backbone of the polymer a factor? And so in this case with PMA, we've taken two forms of PMA, syntactic or atactic PMA, where the carboxylic acid groups are either randomly or are either structured so they're on opposite sides of the backbone, or a mixture of random orientation, syndiotactic. But the isotactic is a polymer where you have the carboxylic acids all on one side, more fixed in space. And so there is a little bit different behavior in the bulk. This is water soluble at low pH. This is not water soluble at low pH, but if you take it up to high pH and then lower the pH, you can make it water soluble when you reprotonate it. So, and 10 to 30% of it is deprotonated from 4 to 6, pH of 4 to 6, going from a coiled to an extended. So again, this is a more fixed orientation of the backbone. This is more regular form of orientation, isomers on the backbone. Okay, so both forms, and so I want you to think about now which might perform differently at the interface. We find now at pH of 1.5, actually both of these, both with the more random structure as well as the fixed, give the same carbonyl stretching modes. And in fact, what you see is really can break it down into two major regions or two major parts of the distribution. We know that the carboxylic acids have a range of distributions of solvation with water, but these two peaks give us a way of thinking about that. And so we believe that this carboxylic acid is has more of a water-rich environment, and this has more of an oil-rich environment. But nevertheless, you see if you do this sort of pH curve, both of them drop off very sharply at the same pH of around 4.5. Oh, gosh, I keep doing that. And so if you look in the CH region, you find very similar, strong some-frequency signal, strong orientation for both CH and carbonyl groups. And so the environments are somewhat the same, as well as the interfacial adsorption. But the dynamics are different. The dynamics are very different. So what you find is that for the SPMA, over time, you have accumulation, again, of the first, I think I need to just go to the key. What you find is that the first layer goes down oriented and then random orientation, and that's why you get this continued adsorption. Okay, so that's with the SPMA. But with the IPMA, you only get that one thin layer. Only that one thin layer goes down and nothing more. You never get the random accumulation. You're never able to get that nestling in of the next layer of polymer. And so the interfacial picture that we have is that for the SPMA, because the carboxylic acids are on both sides of the polymer backbone, that the next layers can go down fairly readily. But when you start to put all the carboxylic acids on one side, you aren't able to get that interaction between the other polymers going down, because now in the aqueous phase, it looks more like a very polar polymer when the polymer tries to nestle in. And so the next, our molecular dynamics simulations show this behavior very nicely. And so this is now the polymer here on the side over here in the water-oil interface. And so when you look at the movie, what you see is the polymer goes down. And when it ends up, you see that the carboxylic acids are largely in the water phase. And so it makes it look like a very polar polymer to anything else that wants to go down. If you want to see this, rather than the dynamic picture, more of the static picture with rotation, you can see that here. This kind of makes me seasick when I look at this, actually. But the whole idea is to be able to show that actually the carboxylic acid modes are more likely to stay in the aqueous phase. When you get the movies for the mixed polymer, for the polymer that has carboxylic acids more randomly distributed, don't show this at all. They actually show quite a bit of coiling of the polymer, but I couldn't bring those movies because they last way too long. We haven't cut them down yet, but it's completely consistent with that view. Okay, so how does charge density or charge cooperativity play a role in this adsorption? To do this, we decided to test polymers of different chain lengths. And so the idea behind this is to take polymers that are very short, so that, for example, there are only 36 carboxylic acids per polymer unit, small, more surfactant-like molecule, versus a very large, flexible coil, which can have a lot of freedom of motion to get carboxylic acid modes in different segments that are there. We keep the same number of monomers there, same number of carboxylic acids in the solution, just have more surfactants versus a smaller number of the larger flexible coiled surfactants. And some very interesting results have come from these studies. So for the small units, you get with this very similar to what we got before, and this is for not isotactic, but the atactic, syntactic polymers. What you find is that, again, you get kind of two environments, a water-rich and an oil-rich environment for the carboxylic acids of the polymer. And interestingly, as far as the pH dependence, the oil-rich environment has more gradual, whereas the more water-rich ones sharply fall off, indicative of some type of cooperativity that's happening between the carboxylic acids in the aqueous phase. And so the picture with this system is that for these small ones is just as before, where you have a highly oriented first layer, and then you have disordered subsequent layers of accumulation as seen by the surface tension measurements, which I haven't shown here. But there still is desorption at a pH greater than 5. Large PMA shows something very different in terms of the pH dependence. What you find is that at a pH of 5, there is no adsorption at all. And then when you get to a pH of 4 to 5, you only get one layer. And then when you go down to 2 to 4, you get a thin layer and random accumulation over time. So let's look in particular at this intermediate region of 4 to 5. The time dependence in the sum frequency signal is very striking. What you find is that what you don't pick up in the surface tension measurements is that a thin layer of absorbed PMI at 4 to 5, remember it's just one layer, but the sum frequency signal for the CH2 goes up and then comes down, and CO comes up a bit and goes down. So it goes to the interface with some ordering to it and does not come off, but takes on more of a random orientation. And so what we believe is happening is that it first goes down, but then with time, there are disordered segments because of this collective interaction between the carboxylic acids, which can induce each other to dissociate more readily when they're near each other. And so those segments tend to go into the aqueous phase. So you get ordered patches of the polymer, but with time, there's more disorder that grows in. So we believe that this is because of these collective interactions between the carboxylate groups, which actually are responsible for this, whereas the smaller PMAs, they can't do that because it's just single chains. They can't get this sort of buildup inside a polymer that changes the solubility of the polymer itself. So the last little story is what happens for polyelectrolytes when you add metal ions in solution. You know, metal ions and complexation with macromolecules is a huge issue in biology as well as in environmental studies, especially when you talk about heavy metals complexing with humic acids and so forth, which are large macromolecules with a lot of carboxylic acids. So rather than through all the data with this, let me just summarize what we found. The test case for this is with IPMA, because what we really wanted to do was be able to be in a situation we were really only looking at one layer going down and not the multiple layers. And so with IPMA, the test case is to look what happens when you add these ions under the condition where you would have only one layer going down, or under the conditions where you're at a higher pH where nothing would go down. So remember this, pH less than 5, something there, pH greater than 5, nothing there. What we find in this case is when you throw calcium into the solution, you actually get strong adsorption of the polymer at high pH. And so not only at low pH, but also at high pH. And so what you have here is just calcium chloride concentration. What you find for pH greater than 5 is the signal first goes up and then sort of levels off. But what it means is that the carboxylic acid now is coming to the interface when it complexes or is influenced by the calcium being there, and so that the electrostatic or charge screening induces the adsorption. You see a very narrowing of this peak in this region, and this is the carboxylate. Remember, we never saw that before. Now we see it very strongly. I don't show here that we also see the carboxylic acid, which also shows up ordered at the interface. So it not only induces this guy to order, but at a pH around 5 and 6, where you also have some carboxylic acids there, they become ordered too. So very much narrowing of the peak, and also a shifting as you see more and more binding. So what we find is that potassium shows a somewhat different effect. Well, calcium induces this adsorption, we believe, by increasing the hydrophobicity of that chain, and so that through dehydration of these carboxylate groups. But potassium just is more of an electrostatic interaction. It's not so much of a complexation. It does induce some adsorption, but not nearly to the level of calcium. But what's even more interesting is you go now to look at the concentration dependence of these observations. And what you find is summarized here. And again, this is at a pH of 6, so it's higher than the adsorption would have occurred before. At this very low calcium concentration, we believe that partial dehydration induces the adsorption of the IPMA. But as the calcium increases, this ordering and more complexation with the calcium induces increased hydrophobicity. And now what we also start to see are water molecules show up in the spectrum that are oriented, because it now is starting to change the conformation of the polymer itself and the hydrophobicity. But at excess calcium concentration, almost complete coverage of the interface occurs. And we believe that what we observe at these very high concentrations is calcium actually bonding to a couple of carboxylate units, not just one. And that certainly shows up in the spectroscopy and changing of the behavior. And so what we find in the time-dependent studies at these high calcium concentrations is first that you have the polymer, which then absorbs with a bit of calcium, with the calcium bound to it at the interface. But then over time, you see a reordering that's clearly evident in the spectroscopy, that none of this is evident at all in the surface tension measurements at all. So the surface tension measurements, which are traditionally used for studying these, are completely invisible to this type of reordering and adsorption at the interface. And in fact, at the high calcium concentration, it takes about 20 hours before you finally get a stable configuration. So there's a lot of jostling around and bonding that occurs as you get to these high concentrations. So that's my story. Take-home messages. This interface provides a unique platform for macromolecular assembly. First of all, that interface has interesting oil-water interactions, which leaves a strong orientation and an interfacial potential that can play a big role in anything that goes to that interface, including nanoparticles, macromolecules, and surfactants that we've studied. And the assembly depends on a number of factors, as I've talked about: interfacial field, polymer charge, how the carboxylic acid units are spaced, hydrophobicity, chain length, and conformation. And also that metal ion polymers interaction can play a big role in this too. And so now what we're doing is to go on to study some other very interesting polyelectrolytes, as well as combining surfactants with polyelectrolytes, and surfactants tend to enhance the absorption of these polyelectrolytes. And the final slide, the most important slide, acknowledging our financial support and also the students involved in this project. Of course, this is what it looks like right now in Eugene, except a few rain coats and umbrellas, which aren't shown. Ellen Robertson did all of the experimental studies I showed you. It's her thesis project, and she's defending in May. She's a phenomenal student, and she's done it all, even driving it. And Nick Valley, if any of you for Northwestern, you might, or Notre Dame, you might recognize Nick. He's the postdoc that's been working on the molecular dynamics simulations. And they always make me show this one, which is the Halloween shot of everyone. The group decided they would all dress as animals, but the research advisor did not get the memo. So back to the group. Thank you all very, very much. I can't tell you how honored I am to be chosen for this award, and I do mean that sincerely. I also want to acknowledge a number of you in the audience that have been friends for a very, very long time, and students that I've had the pleasure of working with. So thank you very much.
Questions?
Thank you. Salt in the organic phase? No. There's a very good chance. What I'm concerned about is that with the ions is that some of those ions that we've used, we found they've had some impurities in them, and we're really sensitive to impurities. So we have to play around with those more. But I think your point is really interesting, and you've worked in this area for a long time, to see how that might turn it around. We just haven't gotten there yet, and also to be able to separate out their spectral contributions from everything else. John.
You know, as I do, that when you use lanyard films and you put in a divalent metal, you immediately interact with the tube. But that's because they move around so fast. So you're thinking the polymer actually impedes the motion of the carboxyl groups, so that it takes a while for them to get together to interact with the calcium?
I think it's, John, that's a good question. I think it's more that I don't think it impedes it. I think the calcium binds, but then the polymer moves around in order to lower its energy. And so it's actually what's moving around and then changing its structure. So I think actually the binding happens quickly. I think it's the polymer fussing around with what to do to lower its energy.
So your system where the SFG signal increased and then decayed, it came down order and then some kind of disorders. What's going on there thermodynamically? Is there some kind of
Well, I think it's not easy to, unfortunately, it's not easy to do the thermodynamic measurements on this because of the fact that we'd like to be able to do temperature-dependent studies, but it's really hard because the organic starts to evaporate or boil, and then icebergs form at the interface if you go too cold. But I do think that there's more of a very slow phase transition that's happening that causes this change in the structure. You know, we use a lot of the literature of these polymers in bulk solution to try to understand what's going on at the interface. And a lot of the way that we think about this in terms of changing its ordering is somewhat consistent with the phase transitions that they see for these polymers in the bulk phase, but we just can't get at those types of numbers. And so that's why we tend to go more towards seeing if we can do the MD simulations to get a more in-depth picture. But we would love to be able to do that.
Geraldine, what is the impact of the calcium ions on the surface tension?
Oh, good question. What's the effect of the calcium ions on the surface tension? Very little. Really? Yeah. Very little compared to what you see here. I mean, with any kind of a surfactant. Yeah. In fact, we've done a lot of studies with looking at how the ions, those calcium ions, change the water structure at the interface. And it changes it a little bit, but not very much. Not certainly to the level that you might think.
You might think that the calcium would be localized on one side of the interface, and that would give you a very large dipole.
Well, the calcium does come in. What you see when you add calcium to the organic water interface is what you do see is oriented water at that interface starts to lower its orientation and become more random because you basically have sort of reduced that field that's there. And so that's what you mostly see. It's actually much stronger effects at the oil-water interface than you would see at the air-water interface, interestingly. But it's really small. It's really subtle.
Other questions?
Yeah. Oh, you mean so with those two different types of carboxylic acids there on the polymer, you're asking is there, and you see if you could see them spectroscopically, is there any relationship with their intensity to? Do you mean their intensity to the to its what form it would be in terms of how much, what percentage you would have as? It's really tough. That's a really good question, and it's very tough to get quantitative numbers for how much stuff is there based on some frequency signal. And so that's why we use a lot of the surface tension data to get us more quantitative information. But as you see, the surface tension is limited in seeing these very subtle changes. And so and the other difficult part is that for these, because the carboxylate doesn't show us any ordered signal, it's not just how much stuff is there, but is it ordered. And so I think with the carboxylates, they're actually not ordered. The carboxylic acids, they are ordered, but if the carboxylates are there, we do see, I must admit, we do see a tiny signal at about pH 3, but it's just so small that it's really hard to even monitor. So your question's a good one.
Thank you very much.
Right, thank you.